The quantum computing foundation quantum algorithms operate within the framework of quantum mechanics, which fundamentally differs from classical physics. At its core, quantum computing relies on qubits, quantum bits, that can exist in a superposition of states simultaneously, unlike classical bits restricted to either 0 or 1. This property allows quantum computers to process vast amounts of data concurrently, enabling parallel computation at unprecedented scales. Entanglement further enhances this capability by linking qubits in ways that classical systems cannot replicate. Superposition enables simultaneous processing of multiple states, drastically reducing time complexity for certain tasks. Entanglement creates correlations between qubits, allowing instantaneous state updates regardless of distance. Pioneering quantum algorithms, a handful of groundbreaking quantum algorithms have redefined what is computationally feasible. Among them, Shor's algorithm stands out for its ability to factorize large integers efficiently, threatening existing cryptographic protocols based on RSA encryption. Grover's algorithm represents another milestone, offering quadratic speedup for unstructured search problems. This has profound implications for database searches and optimization scenarios previously constrained by linear complexity. Shor's algorithm, breaking classical encryption developed by Peter Shor in 1994, this algorithm leverages quantum Fourier transforms to solve integer factorization in polynomial time. Its implementation hinges on finding the period of a function derived from modular exponentiation. The practical significance lies in its potential to render widely used public key cryptosystems obsolete. As a result, post-quantum cryptography initiatives are gaining momentum globally to develop resistant alternatives. Grover's algorithm, enhancing search efficiency. Lloyd Grover introduced his algorithm in 1996, demonstrating how quantum interference can amplify probabilities of correct answers in search spaces. It achieves a square root reduction in query complexity compared to classical methods. While not providing exponential speedups, Grover's approach remains valuable for optimizing combinatorial problems and accelerating brute force attacks on symmetric ciphers when implemented on sufficiently powerful quantum hardware. Applications across domains. Quantum algorithms find application in numerous fields, reshaping industries through enhanced computational efficiency. In finance, they enable rapid portfolio optimizations and risk analysis simulations that would be intractable for conventional systems. Healthcare benefits significantly too, with drug discovery processes accelerated via molecular simulation algorithms capable of modeling chemical interactions at atomic levels with unparalleled precision. Optimization problems. Reimagined combinatorial optimization problems plague many sectors, from logistics to manufacturing. Quantum annealing techniques offer promising solutions by exploring solution landscapes through quantum fluctuations rather than sequential evaluations. D-wave systems. Quantum processors exemplify this approach, tackling instances of NP-hard problems like traveling salesmen and scheduling tasks with measurable improvements over classical solvers. Cryptography's quantum future. The threat posed by Shor's algorithm necessitates immediate action toward developing quantum-resistant cryptographic standards. NIST initiated a global competition in 2016 to identify secure post-quantum algorithms, currently evaluating candidates like lattice-based and hash-based schemes. These efforts aim to transition infrastructure away from vulnerable RSA and ECC systems while ensuring compatibility with legacy technologies during the transitional phase. Challenges in implementation. Despite theoretical promise, realizing functional quantum algorithms faces significant hurdles related to error rates, decoherence times, and scalability constraints inherent in current quantum hardware architectures. Noise-induced errors pose substantial barriers, requiring sophisticated error correction codes that demand extensive overhead in both physical resources and operational complexity. Error correction complexities. Topological quantum error correction codes require thousands of physical qubits to encode single logical qubits reliably. Such resource demands severely limit the feasibility of implementing large-scale fault-tolerant quantum computations. Research focuses on improving qubit coherence times and enhancing control fidelity through advanced materials engineering and novel fabrication techniques aimed at minimizing environmental noise impacts. Scalability limitations. Current superconducting qubit arrays face spatial constraints limiting interconnectivity essential for executing multi-qubit operations efficiently. Overcoming these requires innovations in chip design and cryogenic packaging strategies. Alternative approaches explore photonic qubits and trapped ions as potentially scalable platforms, though they present distinct technical challenges regarding stability and integration with digital electronics. Evolving research directions. Ongoing investigations continue expanding our understanding of quantum algorithmic frontiers, uncovering new paradigms that push beyond established models while addressing persistent implementation challenges. Hybrid quantum classical algorithms represent a growing area of interest, combining strengths of both computational worlds to address real-world problems incrementally until full-scale universal quantum computers become viable. Quantum machine learning innovations. Integrating quantum computing with machine learning opens exciting possibilities for pattern recognition and feature extraction tasks. Variational quantum eigensolver (VQE) algorithms demonstrate potential for solving eigenvalue problems central to many ML applications. Early experiments suggest hybrid models may surpass classical counterparts in specific cases, particularly those involving high-dimensional datasets or nonlinear relationships difficult to capture using standard neural networks. New frontiers in algorithm design. Recent breakthroughs include developments targeting approximate counting and sampling problems using novel amplitude amplification techniques. These advances pave the way for efficient solutions in areas ranging from statistical inference to probabilistic modeling. Additionally, researchers investigate quantum walks, analogous to random walks but exploiting quantum properties, for improved graph traversal and network analysis algorithms with wide applicability in social media analytics and cybersecurity. Industry adoption trends. Leading technology companies actively invest in quantum algorithm development, recognizing its strategic importance despite ongoing technical limitations. IBM Q Network includes over 100 academic institutions and businesses collaborating on quantum software advancements. Microsoft's Station Q pursues topological qubits as part of its long-term vision, emphasizing robustness against decoherence factors that hinder other experimental setups pursuing different qubit realization pathways. Cloud-based access models. To democratize access, cloud providers now offer remote access to prototype quantum devices. Google Cloud Quantum and Rigetti Forest allow developers to test algorithms on actual quantum hardware without requiring on-site installations. This accessibility fosters innovation by enabling broader participation from academia, startups, and independent researchers who might otherwise lack direct exposure to cutting-edge quantum facilities. Educational initiatives and skill development. Universities worldwide integrate quantum computing modules into computer science curricula, preparing future generations of programmers for upcoming shifts in algorithmic paradigms. MIT OpenCourseWare provides free courses covering fundamentals through advanced topics. Online platforms like Coursera host specialized programs focusing on quantum algorithms alongside complementary disciplines such as linear algebra and probability theory, crucial for mastering this emerging field effectively. Ethical considerations. As quantum algorithms progress toward commercial viability, ethical concerns surrounding privacy protection and national security emerge prominently. Governments must balance technological advancement against risks associated with unauthorized surveillance capabilities enabled by quantum decryption powers. International cooperation becomes imperative to establish norms governing responsible usage while preventing monopolies forming around proprietary quantum technologies that could disrupt global information ecosystems unfairly. Future outlook. Although still in early stages, continuous advancements suggest we're approaching critical inflection points where practical advantages materialize across various applications. Continued investment in foundational research promises unlocking untapped potentials hidden beneath layers of theoretical abstraction. The journey ahead involves navigating technical obstacles collaboratively, fostering interdisciplinary dialogues, and cultivating talent pools equipped to drive next-generation innovations shaping tomorrow's computational landscape profoundly. Conclusion: quantum algorithms signify a paradigm shift in computation, challenging conventional wisdom about problem-solving boundaries. Their theoretical elegance combined with tangible applications positions them as catalysts for transformation across scientific disciplines. For practitioners engaged in algorithmic studies, staying informed about evolving methodologies offers opportunities to contribute meaningfully to this rapidly advancing frontier, influencing trajectories of future technological revolutions positively. HTML